Okay, good afternoon. So today we'll try to finish up I/O subsystem and then hopefully get started with file systems. So last time we discussed hard disks. The final topic to discuss about hard disks is scheduling basically their requests. So the requests come in. So inside your hard disk, you're going to be having a queue of requests. Now the controller can look at the requests and potentially schedule them. The easiest way to schedule is to just do first come first serve. This is going to be fair because we're not prioritizing anybody over anybody else. Any request that was generated first gets answered first. Now, unfortunately, this is not good in terms of performance. Let's say this is your disk, and let's say your first request in outer circle, and then you get another request in inner circle, and then you get another request in an outer outer track. So, and then another one here in inner tracks. So what happens is that the head keeps moving back and forth. So the head comes back and forth to answer these requests. I should have done a better job in showing this. In reality, head just moves back and forth, right? So the head has to first be on this track, and then potentially, I'm just making it up. So going from this track to this track, and then going from this track to this track, and then going from this track to this track. So the arm is moving back and forth between these tracks, and that is adding a lot of latency. So it's not good with regard to performance. The second approach that we can take is, well, wherever the arm is, whatever the head is, whatever track we're looking at, we can look at all the requests in the queue and then get the request that is closest to the current position of the head. So this is shortest seek time first. We look at how much the head should seek for each one of the requests, and then we try to minimize that. This way we're minimizing the movement of the head and the arm. Now this will definitely help with the performance. It'll give us better performance, but it comes at a fairness cost, because you might actually, for example, if this is the disk and then you get a lot of requests on these outer tracks, then if you have a single request in an inner track, so this single request could get starved because the arm is keep moving here between these tracks, and it never seeks to this outer track. So this is very good for, so the first one was very good for fairness, bad for performance. This one is really good for performance, bad for fairness. So can we find middle ground? One approach that has been proposed is basically doing a scan. So with the scan, what happens is that the head, the arm moves from the outer track to the inner track and then goes back from the inner track to the outer track. And as the arm is moving, any request that comes under the track, any request that is on a track that is currently under the arm under the head, it will be responded to. So looking at this figure, we're going to do first the first one because it's in the outer track. Then we move on to number 2. Then we move on to number 3, and finally we do number 4. And then on our way back, we do 5, we do 6, and then at the end we do number 7 as the arm is going back. Now this avoids the starvation because the arm is covering all the tracks. It has low seek time because we're just moving in one direction, and any request that comes to us will answer. However, it's basically unfair because we are favoring the request in the middle tracks. The reason is, let's say the arm moves slightly from the outer track, and then you get a request here right after the arm moves past your track. It's kind of like when you miss a bus, so you come and the bus just leaves the station. Now, how long should you wait for the next bus? So in a scan, you have to wait for the arm to go all the way down to the circle, to the center, and then come back. So if you are a request on outer circles, outer tracks, you have to wait for the entire diameter of your plater to be covered by the arm. Now, what about if you're here? If you're in the middle of the disk? So if the arm passes you right before you come, then you have to wait for the arm to go all the way down and then come up. So you are going to wait a shorter amount of time than someone who has come maybe potentially before you, and they have to wait a lot longer because of the distance, because of the way that this algorithm works. To address this, people have come up with an alternative. It's called CSscan. So CSscan, what it does is it goes in one direction to the center. Once it reaches the center, it fast tracks back to the outer section. So on the way back, you don't satisfy any request. You just come back really fast and then do the scanning again. So you're doing scans in one direction only. And now, this is much more fair to everybody, so everybody will wait the same amount of time. It's just a little bit slower, right? Because on the way back, we're not doing any requests. So again, the previous example, we do 1, we go 2, we go 3, we go 4. Let's say by the time we get here, we already have these 3 requests. So in a scan, we would go back and do 7 first. So 7 would be our 5, 6 would be our 6, and then 5 would be our 7. But in CSscan, we just fast track back to the outer track and come back. So this guy becomes number 5, this guy becomes number 6, and then number 7. Now, there is all sorts of optimizations on this CSscan to make it even better performance-wise. Now, one of the optimizations that has been done is CSscan, which allows for consideration of rotation time as well, not just seek time. So you still want to move in one direction, but then you want to allow some backtracking if you can optimize the time. So here is an example. So let's say this is number 1. if you go with the scan, you're going to go from number 1 to this guy. So this becomes number 2 because it's in the next track. But what is going to happen is, after you read number 1, you move the head here to the next track. Now you have to wait for a long time for the next sector that you want to read to rotate to where the head is. So the seek time is going to be fast because we're going to just seek to the next track, but then we have to wait a long time for this sector over here to reach the head of the arm. So we're going to pay a lot of rotation time. Now, alternatively, what we could do is we could do this. Instead, we can do this optimization. We seek 1, we then move the arm down here. By the time that we seek to that track, number 2 has rotated under the arm, so we can read number 2 immediately. And by this time, probably number 3 is here. Then we come back to this track, and by the time we reach back to that track, number 3 has reached us. So this long rotation, instead of we waiting for it, we just went down, did number 2, and then come back, and then do number 3. So some people say this is for reverse, some people say this is for rotation, but you're actually doing both, right? You're considering rotations, and based on that, you're allowing some reverse scanning as well, because we're going backwards. So we go forward for number 2, and then we come backward for number 3. But then you want these movements will be obviously minimized. These you're not going to go all the way to the center and then come back, because that probably the time that it takes for you to do that seek, a complete rotation has happened. So you're not going to do those, but you might actually do a small seeks inside and then towards the center and then come back. This is called RC scan. Now here's a graph. On the x-axis, I have the track number, and on the y-axis we have time. Now let's assume that this is the order. So this is number 1 on the queue, number 2 on the queue, number 3 on the queue, and let's assume that these numbers are the track numbers for these requests. So initially, let's assume that the head is track number 53. Then it has to seek to track number 98. It takes some time for it to reach this track. Then it has to seek to number 187. It takes time for it to seek to this. And then it has to come back to number 37, and so on and so forth. So what you see is that you actually are doing this again and again and again. So this is what FCFS does. What about scan? So let's say head is at number 53. You scan in one direction to get to the center, and then from the center you scan towards the outer circle. So you basically don't care about the order in the queue. You just do your scan, and as you're doing the scan, you just grab the requests that are in the order that are closer to the head. And then this is CSscan, where we only do the requests in one direction. In this example, we're doing them in the direction of from the inner circle to the outer circle. So we do in this direction, and then immediately afterwards we go from the outer track to the inner track, and then do this again. And as you can see on the way back, we're not answering any requests. We just do it fast so that we can scan again. So final notes on disk, the best performance you can get out of a disk if you read sequentially from your disk. The disk is very inefficient. So if you don't have many requests, it doesn't make sense to do any optimization because already everything is slow. So, adding, saving a little bit of time in doing optimizations doesn't really matter. However, if things are busy, if you get a lot of requests, then you might want to do some optimizations, right? For example, the algorithms that we saw with CSscan, with CSscan, and so on and so forth. You might want to do some optimization if you have a lot of requests. If you're busy, it might make sense to do some optimizations. Yeah, okay, so not much left to discuss. Now, the next, we're going to talk about flash memory. So the NAND, so in 1999, flash memory replaced these rotating magnetic disks, and we just replaced them with a battery-backed DRAM, right? We just got a DRAM. We put a battery to always keep it on. Later on, in almost a decade later, we started using NAND cells to store different number of bits in a single flash cell. Sometimes 2 or 3 3-bit cells in a flash memory. Now, I guess I'm gonna just gloss over these. The physics of it probably doesn't really matter. We can use this time to talk about operating system stuff. So I'm gonna move from these. I'm not gonna talk about the physics of it, how read and writes happen on a flash cell. All I'm gonna say is usually the unit of reads and writes on a flash is a page. So the name that they have chosen is page. Do not mix this up with the pages that we talked about in virtual memory and physical memory. These are flash pages, and they might have different sizes than your operating system or your x86 page size. As a reminder, with magnetic disks, the size of the unit of data transfer was sector. Here, the unit is flash page. Reading data off of flash is pretty straightforward and easy, and you can do it with low power. It's kind of just reading from a transistor, so it's quite straightforward, fast, easy. Writing, however, to a flash cell is not that easy. So when you want to write to a flash cell, the first thing you need to do is to clean it. Whatever it stores already, you have to clean it. Now, cleaning a flash cell requires a lot of power. So you have to put a lot of voltage on top of the cell to clean it, to erase it. And once it's erased, then you can write to that flash. And we'll see how this is going to cause us some problems. Now, the upside is that there is no moving parts, so no rotation, no seek time. These are the good things. And as a result, it's going to give us many things. So just eliminating these moving parts, it's going to give us low power. It's going to give us more reliability because, in the old, in HDDs, if you move your, for example, your HDD while it's working, the head could scratch your platers and cause data corruption. Or maybe the head moves slightly on a different track and then you read something that you are not actually wanting to read. So a lot better resilience to errors and faults. The only difficulty with Flash is its writes. So not only they require a lot of power consumption, but also Flash cells have limited number of times that you can write to them. And this is because the number of times you can erase a cell is limited. The voltage that you supply to erase a cell is a lot, and it kind of distorts the cell. And if you keep doing it to a cell, after a while, it loses its. It doesn't respond to it anymore. The Flash cells are dead after a while. So usually there is a life cycle for each Flash cell, the number of times you can write to it, and after you pass that, then the Flash cell is no longer reliable to be used. So they have a limited life cycle. So this limit on writing is going to show up multiple times. The one is in the timing, because it takes time to erase a cell and then to write to it, and also in terms of the life cycle. So these are the two constraints that we'll see how Flash or SSD device providers have addressed. Now, reading is pretty easy. It's kind of like reading from your DRAM. It doesn't really matter where you want to read, because there is no rotation, there is no seek time. So you just send your address on the address bus, and then you can read from those cells. It's pretty straightforward. So random reads and sequential reads equally are fast. As I mentioned, the unit of reading is a unit of data transfer is basically a page. Let's assume that your page size is 4 kilobyte, your Flash page size is 4 kilobyte, and let's assume that you have a SATA connection to your SSD. Now, usually the range of SATA data transfer is something between 300 to 600 megabyte per second. This means that because we don't have any overhead in terms of rotation or seek time, all we have is just data transfer. So the moment you give me an address, I can read it for you. So now you can actually calculate the time it takes for you to read a single page on a device with SATA. It's going to be about 10 microseconds. Now, this is a stark difference between Flash and HDD. If you remember, just a seek time, just average seek time in HDD was something like 4 microsecond. So from 4 microsecond down to 4 millisecond down to 10 microsecond. That's order of magnitude faster. And I mean, I don't know how much you guys remember or how much you guys back in days worked with HDDs. I remember from like a normal desktop you had, if you wanted to restart it, you could just go and grab a cup of coffee or make make breakfast for yourself. That's how long it would take, like 5 minutes, 10 minutes it would take for the system to go down and then come up. because reading from HDD was just painful, slow. Now with a flash, today's systems you restart within a few seconds, your system is up and running, and this is basically the reason. We reduced the latency of a read from 4. I mean, in a random read we did it last time, it was like 9 point something millisecond in a pretty fast device. We have brought it down to 10 microsecond, 1,000 times faster. Okay, so the latency is basically the queuing time, the controller time, and the transfer time. So with HDDs, we also had the seek time, plus we had the rotation time. So we have eliminated these altogether, right? Okay, so reads are good. How about writes? Writes are not that easy to handle. Writes are complex. Now, the main reason for that is, sorry guys, give me a second. Excuse me. So with writes, as I said, you have to first erase the cell. And erasing a cell requires high voltage. And this, first of all, damages the cell. So it limits the life cycle of SSD cells. Second of all, to avoid making cells dead sooner than other cells, you might want to do some notion of load balancing when it comes to writing to your cells. Now, if you, for example, have a file that keeps being updated by the user, so let's say there's this database that keeps getting updates. If you keep writing the updates on the same cell again and again and again and again, you will eventually lose that cell. And this is kind of bad because then, other cells on your system are still working and then one or a few cells are dead. So you probably want to do some notion of load balancing using those cells that haven't been written to make sure that the number of writes on all cells are at any given time are, kind of equal. Now, the other constraint that we have is you cannot erase a single page in flash disk. Now, to be honest with you, I don't exactly know why, but for this, we're going to listen to the device. This is kind of like a physics and magnetic or electro whatever. So the unit of erasing, when they want to erase flash cells, they erase a block which consists of a bunch of pages all together. So when they want to apply that high voltage, they don't just apply it to a single page, they apply it to a block of pages. For example, like in this in particular photo in this slide, to 64 pages. Now, let's see how we can deal with this with these constraints. I'm gonna gloss over this one and then I'll come back to it. So let's assume that that you have two blocks here, block X and block Y. Let's assume that initially both of them are free. Then you write A, B, C, and D. So this is the first thing you're gonna do. You're gonna write 4 pages to your SSD. Now, because all the blocks, because all the pages are free, I can easily write. Excuse me. I can easily write to free and erased pages. So I write A, B, C, D. Now let's say later on I write E, F, G, and H. So I write 4 new pages, and then let's say my application reads A, B, C, D, and then updates them. It updates A to A prime, it updates B to B prime, C to C prime, and D to D prime. Now, when this write happens to SSD, as I mentioned, you can't write to an unerased page. So we cannot really go and update A, B, C, D. What we'll do, we'll just mark them as garbage. We say we don't need them anymore, and we write the new values in new pages because again, we can't go back and write on the same page. So we have to find free pages and then write it there. Later on, garbage collector is going to notice that this block has some pages marked as garbage. So then garbage collector wants to collect the garbage. Now, the garbage collector cannot erase these 4 pages by themselves. As I mentioned, you can't erase single pages. You have to erase the entire block. So what should we do at this point? What we'll do is we'll grab the valid pages, the pages that are not garbage. We then write them to some free pages in another block. So in this example, we go to block Y and we write the live pages, the pages that are valid, to empty pages in this block. Once block X is ready, there is no data that we really need, then we can erase it altogether. Because as I said, we're going to erase the entire block. We can't erase single pages. Okay, so this is basically what happens with a write, and due to all the constraints that we have, as you can see, a single write, right? Let's say you had a single request to write this file, ABCD. This ends up being writes here, and then the entire block has to be written again, and then your original block being erased. So a single write could cause a sequence of writes due to this garbage collection and due to the constraints that the flash has. So this is basically called write amplification. When you write a single page, you may end up writing it so many different places due to the garbage collection that we just described. And this basically shortens the life cycle of your SSD, obviously, because you have a limited number of writes that you can do to your entire SSD. And now a single write is creating a tsunami of writes, and that's basically bad. It also consumes a lot of bandwidth, right? So you just wanted to write your file, but what ended up happening was a complete block had to be copied, and then a complete block had to be erased. So this consumes bandwidth from the controller, right? Now, it will then depend. You will get this asynchronous, heterogeneous writes. So some of your writes are going to be fast. If you have empty pages, you just go and write. But then some other writes might end up taking a lot of time because you have to wait for the garbage collector, for example. Now, in essence, the latency is basically your queue time, your control time, the controller time. Here, you might actually have to find a free block. You might end up doing a garbage collection, so on and so forth. And then eventually your transfer time. Similar to reads, it doesn't really matter if you're reading or if you're writing sequentially or if you're writing in a random place, because it doesn't matter. Now, going back to the slide that I just glossed over, all of the things that I just described are done with they're all done by the flash memory controller. So flash memory controller is the controller inside your SSD. It provides this flash translation layer. The reason for us to need this layer that is implemented by the SSD is because from the operating system point of view, operating system knows each file has been mapped to some flash pages. Now, where inside the flash these flash pages are, the operating system has no idea, because the controller, as we just saw, keeps moving pages around. So this requires the flash controller to create this mapping between what operating system knows. So when operating system wants a file, it knows which virtual flash pages this correspond to, and then the controller gets that. So the operating system says, give me flash page number 1. Now the flash controller knows where this actual page resides inside the flash. Maybe it's in a physical flash page 1000, because it keeps moving, right? So we need to have this mapping. It's very similar to the page table mapping that we discussed, but this one is just done by the SSD controller internally inside the device. It just does this transparently from the operating system. Operating system doesn't need to know where pages are, because the flash controller keeps moving them around every time it does garbage collection, for example. The flash controller also has to take care of this wear leveling, this load balancing of writes over all the cells that we have. And then finally, you might actually want to keep some of the pages as a spare pages, because of if, let's say, your cells die, they wear out, you could use those as spare pages. So if you go and buy an SSD that is advertised to have 1 terabyte, it could potentially have internally an extra 100 gigabyte that it's not telling you, and it will be used if some of your pages wear out. Then the flash memory controller can use the spare pages. It's very similar to sector sparing in HDDs. Right, so we talked about this remapping. We talked about garbage collection. The last topic I want to talk about is this kind of like a collaborative garbage collection between the operating system and the flash controller. Now, generally speaking, when your user programs delete some file, the operating system doesn't need necessarily to go and tell the permanent storage that this file was deleted, because permanent storage doesn't care, generally speaking. So operating system could just empty those virtual flash pages or those sectors, and then use them later on for some other file when they're created. Now, this is fine, right? If operating system doesn't tell the HDD or SDD, sorry, HDD or SSD, but if operating system can tell SSD, then SSD can garbage collect those pages. Because of this garbage collection, if the hardware controller knows that some files, some pages are no longer used, it can garbage collect them. But if it doesn't know, then it cannot touch them. So it has to basically move them around so many times. And it's basically not efficient to do this and not tell the flash. So there's this trim command that the operating system could use to tell the SSD that these virtual pages are no longer needed. This file was deleted. Now, if you want, you can garbage collect those pages. So this allows, this will limit this tsunami as we discussed, right? So if the operating system if the hard disk knows that E, F, G, and H are no longer used, it doesn't need to copy them here. So you can just garbage collect them with A, B, C, and D, right? So the trim command comes handy to do some more optimization here. Okay, now let's go through this data sheet from a SSD. This is not that current. I think this is from 2018 or 19. I think it's 19. I updated it last year. 2 years. Last time I taught this course. So this is for a few years ago. Things should not have changed by much. So let's see if we can make sense of the information in this slide. Let me make it a little bit bigger. So first thing to note is this: the interface is PCIe, which we discussed, and the protocol to transfer data is NVMe. So we're using PCIe lanes, and then the way we're transferring data and sending packets and interpreting them is through NVMe protocol. The capacity is the max capacity for this particular NVMe SSD is 2 terabytes. So you can compare this with the 14 terabyte HDD that we saw last lecture. So the capacity is usually less than what an HDD can provide. Now this part is interesting. This is the cache. So if you remember with I actually don't remember the exact number. So let's go back to this the figure that we saw last time. So the cache here was a few megabytes. That was enough for us, 256 megabyte of cache. Now on a SSD, this cache is usually a lot larger. So in this particular example, the size of this cache is 2 gigabytes on higher ends. Now we'll see how this cache comes handy. I'll talk about it when I move down this data sheet. Okay, so the other thing that we might want to look at is the diameter of this. It's a lot smaller than a HDD, obviously. It's a lot lighter as well. Now, if you're reading sequentially, this is how much data you can read from this. It amounts to 3,500 megabyte per second. Compare this to 4 megabyte per second kind of performance you can get out of HDD. And then if you're writing, it's obviously slower. As we discussed, writes are harder to perform, so you're getting less write performance in this case. And as you can see, the larger your capacity is, the faster your writes are, obviously, because you have more free pages to write. So you don't need to search for empty pages when you have more capacity. So that explains why the write performance is slower when the capacity is lower, because you have to search more, you have to potentially do garbage collection, and that slows down. Whereas when you have a lot more capacity, then you can just find some spare and free pages to write. Now, the interesting part comes here, where you have random reads. Now, all of a sudden, the equation changes. So with random reads, you can see that the performance is the throughput is 19 19K IO per second, whereas random writes you can do all the way to 60K IO per second. Now, this is where we can circle back to this cache. So when you're writing to an SSD, you don't really need to go and write to the cells, the flash cells, to tell the operating system that the write is done. You can temporarily write it to your cache and acknowledge this IO operation to the operating system and tell operating system, don't worry, I got it. I will eventually write it to my flash cells. So this is where the cache comes handy. So you write, instead of just going and writing to the cells, which could potentially take time, you write it in your cache and you acknowledge the write, and operating system will move on. This is not true for reads, however. If you're reading, you actually have to go and read from the cell. So reads are true performance and throughput that you get. The writes are kind of like we cheating throughput numbers, because we're just writing it first to the cache and then later on we're reading. And this explains why you need these really big caches in your SSD. Yeah. And then I mean, I'm not 100% sure, but I think this is the number of lanes inside your SSD, the number of active writes that you could do per second. I might be wrong. I'm actually not sure. So sorry if this we need to do some research what QD1, QD32 means. But if I'm not mistaken, this basically means that you have 30. You could do all the way to 32 concurrent writes or 32 concurrent reads per second, or simultaneously at the same time, if I'm not mistaken, obviously. Okay, so that's that. I guess at this point I can show you a video talking about SSDs before moving on. So let me try to bring the video.
Hello, everyone. In this video, we're going to talk about M.2 non-volatile memory express solid-state drives, or SSDs. Now, these drives are relatively new and have only been around for a few years now. And just like regular 2.5-inch SSDs that we're more familiar with, M.2 SSDs also use flash memory for data storage, and they are very fast. But the difference between a regular 2.5-inch SSD and an M.2 SSD is that the M.2 is a totally different form factor, and it connects to a different type of slot. The M.2, which was formerly known as a next generation form factor, is a standard that's used for mounting expansion cards internally. Now, SSDs have dramatically passed mechanical hard drives as far as speed. And this is because SSDs have no moving parts, because they use flash memory for data storage, as compared to mechanical hard drives that use rotating magnetic disks to store data. But in recent years, SSDs have gotten faster and are more capable of moving data at a faster rate. So in order to unlock the full capability of SSDs, engineers needed a new technology to unlock the faster speeds of SSDs. And that's where M.2 and NVM Express come in. Now, prior to M.2 and NVM Express, the latest interface standard that was widely used for hard drives and SSDs was SATA 3.0. And the standard that was used for an interface for software to communicate with SATA was the Advanced Host Controller Interface, which is better known as AHCI. Now, AHCI was developed primarily for mechanical hard drives. It wasn't made or optimized for SSDs, and that's mainly because it dates back to 2004. So it was creating a bottleneck for today's SSDs. The SATA 3.0 bus with AHCI allows data transfer speeds at a theoretical rate of 600 megabytes per second, which is pretty fast. However, M.2 NVM Express SSDs do not use the SATA bus. They instead use the PCI Express bus, which is much faster than SATA. So by using the PCI Express bus with an optimized protocol like NVM Express, these allow SSDs to transfer data at a rate of 3 gigabytes per second, which is extremely fast. So M.2 SSDs with NVM Express is roughly 5 times faster than SATA and AHCI. Now, this speed will vary depending upon what motherboard you are using and which SSD, but regardless, it's still a lot faster than SATA SSDs. NVMe, or Non-Volatile Memory Express, is a communications protocol specifically developed for SSDs. It basically reduces the CPU overhead and streamlines operations, which lowers latency and increases input and output operations per second. Or in other words, it's fast. NVM Express was developed to fully take advantage of the capability of PCI Express storage devices and to perform many of the input-output operations in parallel, meaning that many calculations are done at the same time. A large job is broken down into several smaller jobs that can be processed independently. Now, this is very similar to how a multi-core CPU works with multiple threads, where the CPU cores work independently of each other to perform certain tasks. Another advantage that NVM Express has over AHCI is what's called the command queue. The command queue is a queue for enabling the delay of a command to be executed. So in a nutshell, as commands are sent to a storage drive, it gets into a line or queue.
So here I have to interfere. This is basically the command queue that we talked about implementing FCFS or FSscan or CSscan or any other thing. So the commands are basically telling us where to read, and we have a queue of them, and we can reorder. He here just talks about FCFS, but this is exactly the same command queue that we were talking about a few minutes ago. So, okay, continue.
Queue. Then as each command is finished executing by the drive, it goes to the next command in the queue. Now, AHCI allows one queue with up to 32 commands in the queue, but NVM Express allows 64,000 queues, and with each queue capable of 64,000 commands. So in theory, if you were to max out NVM Express, you can fulfill a staggering 4,096,000,000 commands. The M.2 SSD connects to the motherboard in the M.2 slot. It just slides into the spring-loaded slot and then tightened down with a single screw. And that's pretty much it. There's no other connections to be made. So there's no connection cable or separate power cable. So it's just like an expansion card. Now not all...
Okay, so you can actually watch the rest of this. So I guess the part that we were interested is over. Okay. Give me a second. Okay. So there was an article on in New York Times talking about a quirky study of weighing a Kindle. So basically, when you're writing in a flash disk, you actually have to store electrons on it. So and electrons actually weight. So they did this study that they weighted an empty Kindle and they then weighted a Kindle that was not empty, and they showed that it's just heavier by 10 to minus 9 grams. So yeah, okay. So in summary, the strength of SSD is its low latency, and the fact that it doesn't have any moving parts. It makes it lighter, it makes it more power efficient, it makes it more resilient to faults that are caused by movement, for example. And it has really high read performance. The weakness is basically mostly its price. So it's more expensive than HDDs. I think the price gap is closing. So initially when they came, they were a lot more expensive than an HDD, but I think the price gap is closing. I mean, they're still more expensive than HDDs. You have this asymmetric writes due to the fact that you have to do garbage collection. And then you have this limited life cycle for your flash cells. Again, we're making improvement in all areas, right? Maybe a smarter garbage collection, maybe more life cycle, and then at the same time bringing the expenses down. So these are really changing. If you compare this 10 years ago, it would have been a totally different numbers. So here I have them side by side. As you can see, the access time is a lot faster in SSD. And this is an SSD, it's not an NVMe SSD, it's just a normal SSD. Random I/O, a lot faster, reliability better, no moving part means better energy consumption, and so on and so forth. Okay, so that's that with I/O. So we can then move on to file systems. Yeah, unfortunately, I won't be able to talk about reliability, but hopefully we get to talk about file systems a little bit. Okay, so again, I'm not expecting to be able to finish all the slides on file systems. So best case scenario, I can potentially talk about FAT file system, and then briefly mention FSS and NTFS. What will happen is I'll for those of you who are interested, I'll just refer you to my lectures from fall 2019 or winter 2020, I guess. So that would be a reference if you're interested to. At that year, I don't know what happened. I was just I covered a lot of material. I don't know how, but I've added a lot of extra material, so that's probably why I'm not being able to cover these file systems. But anyhow, okay. So file system is an abstraction that operating system provides for persistent and named data. You probably have seen or used definitely file systems in ECE 252. So here we're going to just look at high level how operating system is implementing file systems. So when data is written, it should persist unless the user tells us that they no longer want the data, and so they want to delete it. The data should be human readable, right? Sorry, the name of the files have to be human readable. So we can't use 0.0x, I don't know, FFCB stuff for addressing our files. We want to give them names that people can use. They want to say go to dev and then, you know, to this folder, that folder, and then give me this foo.text or foo.a or whatever. So for that, we need our interface to use names. It has to be having naming. It has to be able to organize our files in data storage blocks. So on top of that, it has to provide protection. If I write my data and somebody else can come and read, for example, my files, that's not good. So we want some notion of protection and access control, and we also want our data to actually persist. So if I'm writing, I want it to persist until I say I no longer need them. So these are the requirements that we need for the file system to provide. So you've seen files, you've used them in 252. Mainly, a file consists of data with regard to that file and some metadata with regard to that file. basically who owns the file, what is the size of the file, when was the last time that the file was modified, what are the permissions on this file, who can access it, basically. Now, from users' point of view, they have, they look at files as durable data structures. So I'm going to write my data and it's going to stay there in this file forever. From systems point of view, from the operating system, for example, we are looking at this differently. We're looking at, okay, how can we allow users to create these files and access them? So basically, we're looking at the system call interface to allow users to create, read, update these files. And with that point of view, then we really don't care about what is in those files. We're just looking at, give me some number of bytes and I'm gonna just read, or if you want to write, tell me what characters, what bytes you want to write, and then I'll write it for you. If you want to read, I will just read those bytes off of the storage and then leave the interpretation to the application. So the file system view of things is going to be just a collection of data blocks that we don't need to make sense of. We just need to manage them. So from the operating system, we're going to just look at this data as a bunch of bytes. We don't care if it is a PDF or if it is a executable file or if it is a Word file. Although there are some exceptions. For example, here's an example. If you have this user interface implemented by system libraries, then you might want to know that this file is executable, right? If the programmer double clicks on this particular file, you want to start launching the program. So there are certain cases where you might care about what the file is, but from the perspective of the file system, we're just dealing with a collection of bytes and blocks. What are the file access patterns? So you might access your file by saying that give me the next X bytes of this particular file, right? So you might be reading your file and then you can say give me next line, which is something that you probably have done in ECE 252. So you're just doing sequentially going through your file. You could also have random access to your files. Again, you've seen this. You seek to certain byte inside your file. So again, this is something that the interface should support. So you might say, give me the bytes from I to J, not necessarily where I am right now, somewhere in the file. Here is an example. For example, let's say this is an example with the paging, demand paging. Let's say you have this swap file where you store your swapped pages. Now you might want to bring a specific page back to memory, so you want to read it. You kind of do a random access to read that particular page. You also might have content-based accesses, like the ones that, for example, in Mac OS, the Spotlight search is basically a content-based access. You tell operating system, give me all the files that start with foo or end with foo, or give me all the files that are pictures, or give me all the files that are PDFs, or so on and so forth. This is basically what is the flow of accessing files in a system from users' point of view. They create their file, they give it to the file system, and this is the interface for users. Users don't care what's happening behind the scenes. The file system, however, has to deal with the storage, the permanent storage, in terms of where each byte of this file resides. Yeah, okay. So here's a cool study, if I'm not mistaken, from Microsoft Research, that people looked at the metadata of files and studied the characteristics of files for a period of, I think, five. Oh yeah, why am I saying I think? Yeah, for 5 years. And they came up with really interesting observations that you can see in this graph, in these two graphs. So let's look at the first graph. So in the first graph, on the x-axis, I have file size of each file, and on the y-axis, I have the number of files with such size in the entire file system. So basically, the frequency that a particular file has this particular size. And as you can see, and this is from 2000 to 2004, so it's 2 decades ago. Things have changed, definitely. But back in then, most of the files were small. So these large files did not exist. These really small files didn't exist. So most of the files were small. Now, across years, this peaked. So the number of files in the system increased. So we have more and more and more files. So we could potentially expect this to be a growing function of years. So, you know, today you might have millions of files in your file system, whereas in year 2000 you probably had few. Sorry, actually, around those times you had millions, so probably now you have billions of files in your system. But as you can see, across years, the peak didn't change. So you kind of peaked at small files, like 2K files. Now, the second graph in this slide, on the x-axis, I again have the size of the file, and on the y-axis, I have the number of the space that this file consumes in the file system. So basically, this is kind of like a multiplication of. So, for example, if you have a single file that is 1 gigabyte, so this is kind of like it's kind of like number of files with size x times X, right? So this is how much storage goes to files with size X. Well, how many of them do you have multiplied by their size? So looking at this graph, you know that we have a lot of 2K files, but how much does this consume a space? Well, it's going to be 2K times whatever number we have. So in this example, we have 10,000. So we have 10,000 2K. So this is kind of like 20 megabyte. So if you look at 2K, it's not here even. So it's like 20 megabyte. This is how much space these files consume. Now, if you have a single 64 gigabyte file, then it's going to consume 64 gigabytes of memory, just that single file. That single file is going to consume more space than these 10,000 files. Now, as you can see, it's not anywhere here. So the reason this is not somewhere here, somewhere here, we don't have 64 gigabyte files in our system, and this is kind of like average over whoever participated in this study. So maybe there was one 64 gigabyte file across 1,000 users. So they just divided that by the frequency of that file appearing in the system. That's why it's somewhere here. But anyhow, apart from the why of this, let's look at the observation. So the observation here is that the majority of our space, the majority of the space in our storage goes to files that are small, not that small, 2 kilobyte, but then relatively small files of 2 megabyte, let's say. So, and then this peak is actually going, moving in this direction. So it feels like we're having more and more of our, maybe now it's like something like this. So most of our storage is files that are of this size. The other observation that they made was, it seems like there is another peak here. So it's not a single peak graph. So you had this single peak, but then another single peak has happened. So maybe nowadays we have a bunch of these peaks in our data system. It would be interesting for someone to do this experiment again. Now, both of these two experiments, what they show us is that these small files are very common, both in terms of the number of files that we have that are small, and also the amount of storage that they occupy. So most of our storage goes to small files, and most of our files are small files, so both ways. Yeah, I guess I could have explained them here, but nevertheless, so most of files are small. This is first observation. Second observation, large files use a lot of space, but we only have few of them. We only have few of them, but they do occupy a lot. I mean, obviously, if you have a large file, it's going to occupy a large storage. And you know, this observation really shaped a lot of development in terms of file system in years to come. So if you look at the Linux file system, you will see that it's based on these observations. So we're going to do a lot of optimization for small files. The reason is because we think that we have a lot of them. And we're going to be really careful how we store big files because they will consume a lot of space. Now, knowing these is good. Knowing these patterns is good, but we should be aware because it's not always the case that you're dealing with the average case. You also, when I talked about Linux file system, it's really optimized for small files. But then if you have a big file, you're screwed because the file system really doesn't do things efficiently with it because it's mostly optimized for the small files. Okay, so I'm going to stop here. Hopefully on Tuesday next week, we get to I don't think I'm going to finish this, but talk at least about FCF, about FAT, and then just mention about the two other file systems. Thank you for sticking around. Sorry that I went over time. Take care, be safe. We'll talk to you later. Bye.